Everywhere you go in the world, you'll encounter cylinders of gas, such as these ones here. And the hospital is absolutely full of different gas cylinders. There's gas pipelines. And if you work in healthcare, you need to understand gases. This tutorial looks at the gas laws, Boyle's law, Charles's law, and the third gas law, and it looks at the relationship between temperature, pressure, and volume. It's essential material. I hope you enjoy it. An introduction to anesthesiology with me, your host, Pat Nelligan. Understanding gases and vapors. Part 2, the gas laws. Welcome back. In the previous tutorial, I discussed the phases of matter, solid, liquid, and gas, and discussed what a vapor was versus a gas. I then went on to discuss the saturated vapor pressure, boiling points, airway humidification, and the problem of condensation. I'm going to give a lecture on a warm day. I don't want to have large sweat rings under my armpits, so I locate a can of aerosol deodorant. I shake the bottle to make sure that there is liquid inside. I locate the tip, target my armpit, and push down the tip, and gas is released and it solidifies in my axilla. What's going on here? There is a lot of good science in this process. The deodorant is particulate, but it's mixed with a propellant gas. The mixture is pressurized into a liquid in the can. When the tip is pressed, the pressure drops and the gas mix is released. The propellant gas rapidly evaporates. The cool skin then causes the suspended solids to precipitate out. Key to all of this is pressure. Pressure is endlessly confusing because different measurements are used to describe pressure. For example, I have a flat tire and I go to inflate it at a service station, and the machine displays the pressure in my tires in pounds per square inch. Unfortunately, the manual for my car requires that I inflate the tires in kilopascals. We also have measurements on the weather channels in torr and in atmospheres and in hectopascals. And in medicine, we have a bunch of different measurements. Particularly, we use millimeters of mercury for blood pressure and blood gases, centimeters of water for venous and airway pressure, and kilopascal for blood gases. The gas pipelines in the hospital also use bar, which are multiples of atmospheres. So here's a simple conversion. 10 millimeters of mercury equals 1.33 kilopascals. So if you multiply the kilopascals by 7.5, you get millimeters of mercury. That equates to 13.6 centimeters of water. So here's a question. If my blood pressure is 120/70 millimeters of mercury, what is it in centimeters of water and kilopascals? Pause for a moment and do the calculation. The answer is 160/95 centimeters of water, or 16/9.3 kilopascals. Now, a key thing to understand about gases is that they are susceptible to temperature and pressure. Any gas in existence can be turned into a liquid or a solid if the temperature falls sufficiently by cooling it. Gases can be liquefied by applying pressure, making the external pressure higher than the saturated vapor pressure. We know that water boils at sea level at 100 degrees Celsius. That's 101 kilopascals or 760 millimeters of mercury. Here's a scenario. You're having guests for dinner. You have cooked chicken, but you've just been informed that they love ham and hate chicken. You have a 2-kilo piece of ham in the fridge, but they will be arriving in 1 hour. It takes 90 minutes to boil 2 kilograms of ham, and you don't have a microwave. How can you cook it quicker? You can achieve this culinary sleight of hand by using one of these devices. This is a pressure cooker. It was the air fryer of the 1980s. Everybody had one, and they're tremendous devices. Using a pressure cooker, you can reduce the cooking time of a 2-kilogram ham to 1 hour. It does this by doubling the air pressure within the pot to 2 atmospheres, or 202 kilopascals, 15-20 millimeters of mercury. As a consequence, water boils at a higher temperature of 121 degrees Celsius. Now the problem is that this dinner party is being hosted at base camp on Mount Everest. And at base camp, which is at 5,300 meters, atmospheric pressure is 53 kilopascals, or 400 millimeters of mercury, and at that altitude, water boils at 80 degrees Celsius. So my advice at this altitude is forget the ham, eat the chicken. But you're saying to yourself, this is not a home economics lesson. I'm an anesthesiologist. Why does this matter to me? And the reason why this matters is because our hospitals need a staggering amount of oxygen per day. A 300-bed hospital typically uses 10 million litres of oxygen per day. An ICU ventilator can use up to 100 litres of oxygen per minute. A large hospital oxygen cylinder can only hold 10,000 litres of oxygen. Now that seems like a lot, but for our 300-bed hospital, that equates to 1,000 cylinders of oxygen per day. That is a stunning logistical problem, but it was resolved in the 1950s by the introduction of liquid oxygen into medical practice. Most hospitals have these giant thermos flasks somewhere on their grounds that contain liquid oxygen, and they're based on very simple scientific concepts. Oxygen has a boiling point of minus 180 degrees Celsius. Below that, oxygen is a liquid. By pressurizing and cooling oxygen simultaneously, it can be stored very efficiently in liquid form. From this cylinder, the pipeline oxygen for the hospital is derived. The pipeline oxygen delivers oxygen under pressure, and that pressure is 4 bar or 300 to 400 kilopascals. If you're working in the operating room, there is a button on your anesthetic machine called oxygen flush. If you push this button, oxygen gets flushed at 4 bar. This is not the safest thing that you can do to your patient. Anyone who's ever held a syringe in their hand, put their finger on the end and pushed in the plunger will note that the gas inside the syringe will squish down, and then when you release the plunger, it expands again. Gases can be compressed with pressure. For example, the deodorant. And this is known as Boyle's law. By increasing pressure, you reduce volume. Gases can be compressed by cooling and expand by heating. That's Charles's law. That's why you don't want to throw your can of deodorant into a fire. It will explode. So the volume and amount of gas are directly proportional at constant temperature and pressure. Now there is a temperature above which a gas cannot be liquefied by temperature alone. For oxygen, that temperature, known as the critical temperature, is minus 118 degrees Celsius. That means that when you see a cylinder of oxygen in the hospital, that cylinder can only contain gaseous oxygen. It's pure gas. For carbon dioxide, it's 31 degrees Celsius. So you can store carbon dioxide, as we'll talk about later, as a liquid. The important thing about oxygen always being a gas when we're using it around the hospital in cylinders is that the pressure gauge on the oxygen cylinder indicates the volume. If the gauge says half full, the cylinder is half full. And this is important because we transport patients all over the place. We transport patients up and down to the operating rooms, down to radiology. We put them in ambulances and send them to other hospitals. And we need oxygen cylinders to do that. And it's imperative that if you're transporting a patient, you check how much oxygen is in the cylinder. And you can do this with confidence that if the gauge on the cylinder says that the cylinder is full, the cylinder is full. Now, one of the problems with oxygen is that there are different bottles with different colors all over the world. These days, the ISO standard for oxygen cylinders is white. The old standard in Europe and the UK was a black cylinder with a white cuff around the neck. In the United States, the cylinders are typically green or they're silver with a green cuff. I think this is the best color to have oxygen. Nothing else looks quite like it. Everything else is a bit confusing. Carbon dioxide is stored as a liquid. At normal room temperature, it remains a liquid, and I have a cylinder of carbon dioxide at home for my soda stream. This is to make soda water. But in a very hot place, it'll turn into a gas. So my soda stream cylinder will automatically release gas if the room gets too hot so it doesn't explode. But there's a curious thing on this cylinder. It says at the bottom that there are 60 litres in it. What does that actually mean? The soda stream bottle weighs 750 grams when full and 320 grams when empty. That means the carbon dioxide liquid in the bottle weighs 430 grams. So how many litres of carbon dioxide are in the bottle when new? Let's work the problem. 1 mole of carbon dioxide has a molecular mass of 44. Carbon is 12 grams per mole, oxygen is 16 grams per mole, so that's 2 molecules of oxygen, that's 32, plus 12, that equals 44. 430 grams of carbon dioxide contains 430 divided by 44, or 9.77 moles of carbon dioxide. 1 mole of gas contains 22.4 litres. So if we multiply 22.4 by 9.77, we'll come up with the result of 220 litres of carbon dioxide in that soda stream bottle. That's a lot more than 60 litres, isn't it? And if you look carefully at the bottle, it actually states that it can make 60 litres of soda water, meaning that for every 1 litre of soda, there are 3.65 litres of carbon dioxide. No wonder you belch. Nitrous oxide was introduced by Horace Wells in 1844. It was the first anesthetic gas. It's not a vapor. The boiling point of nitrous oxide is minus 88.5, so it's always a gas. However, it can be compressed into a liquid by pressure. And when we have a cylinder of nitrous oxide, it's a liquid inside the cylinder, just like carbon dioxide. The critical temperature of nitrous oxide is plus 36.5 degrees Celsius. So it can be stored as a liquid in cylinders indoors and in temperate climates. But because the pressure gauge only measures the vapor pressure, you have absolutely no idea how much nitrous oxide is in the cylinder because it's principally liquid. How do you know how much nitrous oxide is actually available? Well, you do this by weighing the cylinder, just like carbon dioxide. If you know the weight of the cylinder when it's empty, the additional weight is nitrous oxide. For example, we calculate out that the weight of nitrous oxide in the cylinder is 2.5 kilos. And using the same calculation that we did before, we can now figure out how much nitrous is in the cylinder. Conveniently, nitrous oxide has the same molecular mass as carbon dioxide, 44 grams per mole, because it has 2 nitrogen at 14 grams per mole each and 1 oxygen. 2 by 14 plus 16 is 44. Then we divide the total mass by the molecular mass, 2,500 grams by 44, and that gives us 57 moles total. We multiply 57 by 22.4, and that gives us the total amount of nitrous oxide in the cylinder, 1,272 litres. So this is a really useful calculation to do, and you might be asked this in an exam. Now let's review the tutorial. In this tutorial, we discussed the gas laws, Boyle's law, Charles's law, and the third gas law, and we looked at the relationship between pressure, volume, and temperature in gases, and I explained the critical temperature. We then went on to talk about oxygen storage and nitrous oxide storage. Next time, we're going to talk about Dalton's law of partial pressures. I'll see you then.